Hey everyone, welcome to the video. In this video series, we'll be taking a deep dive on the longest increasing subsequence problem. This is a fundamental problem that is very useful in problem solving, so it would be nice to add to your algorithmic toolset. I'll discuss both the ON squared and ON log n dynamic programming solutions. I'll try to explain the solutions in a way that might help you understand how you might have discovered the solution yourself, as opposed to just sharing the solution. However, I'll start with a disclaimer. If you're in a time crunch for interview preparation, then this video is probably not a good investment for your time. However, if you truly want to understand the ON log n time algorithm, then this video is for you. The longest increasing subsequence problem, or LIS for short, is easy to state. You're given an array A of n numbers, and you're tasked with finding the longest subsequence in A that is strictly increasing. More formally, you need to find k indices in increasing order, I1 to ik, such that ai1 is less than or equal to ai2, which is less than ai3, and so on until aik, while maximizing k. For example, suppose A is 1, 2, 4, 4, negative 5, 6. Then the LIS would be 1, 2, 4, 6. Notice that we didn't choose 4 twice because we require that the sequence to be strictly increasing. Also, notice that the longest increasing subsequence must be in order. So the sequence negative 5, 1, 2, 4, 6 is invalid because the numbers are not in their original order. Now, whenever you see a problem like this, it is often useful to start by characterizing the optimal solution. This is really just a fancy way of saying to imagine the structure of the longest increasing subsequence and try to prove some structural properties about it. To do this, imagine some oracle told us that the longest increasing subsequence is opt, which is equal to ai1, ai2, and so on until aik. Once we've characterized the optimal solution, let's think about its properties. This second step involves guessing part of the solution and seeing if we can find an interesting property about the remainder of the solution. Suppose the oracle that told us the optimal solution was also kind enough to tell us that the last element in the LIS is aik. What can we tell about the solution? Take a minute and think about what other structural properties we can get about opt. Now, I'm sure if you spend some time, you can come up with these two properties. First, since opt is an increasing subsequence, then it must be that aik-1 is less than aik. In addition, it must be that ai1 to aik-1 is the longest increasing subsequence ending at aik-1. Why? Well, imagine there was a longer subsequence that ends in aik-1. Then we can just merge that sequence with aik to get an even longer sequence ending at aik of length at least k plus 1, and it's also increasing, contradicting that ai1 to aik was the longest increasing subsequence. Great! With those observations, this should start tingling your recurrence senses. We just characterized the LIS using another LIS of a shorter sequence. So let's try to set up a recurrence to capture this intuition. Let LIS of I denote the maximum length of an increasing subsequence ending at AI. For example, if A is 1, 2, 4, 4, negative 5, 6, then LIS1 is the longest increasing subsequence ending in A1, which is just 1. And is of length 1. LIS2 is the longest increasing subsequence ending in A2. The longest such subsequence is 1, 2 and has length 2. LIS3 is the longest increasing subsequence ending in 4, and so LIS3 is equal to 3. Similarly, LIS4 is equal to 3, and LIS5, however, is 1, because the longest increasing subsequence ending in negative 5 is negative 5 itself, and has length 1. Finally, LIS6 is 4, corresponding to the sequence 1, 2, 4, 6. Now let's think slowly how we calculated those LIS values. Suppose we know that the LIS ending in A1 is 1, and the LIS ending in A2 is 1, 2, the LIS ending in A3 is 1, 2, 4, and so on until A5 being -5. How can we calculate the length of the longest increasing subsequence ending in A6? Take a second and think of an OFN algorithm to do this using the pre-computed LIS values. I'm sure if you spend enough time, you can come up with this strategy. You will start with a pointer j from index 5 and go backwards. In each step, you can check if aj is less than 6, and if it is, then we add one new candidate for the LIS, ending at A6, which is the LIS ending at aj plus 6. In the end, you choose the candidate that is the longest, and that must be the longest increasing subsequence ending in 6. In this case, it's of length 4. With that intuition, we're now ready to write some recurrences. Earlier, we defined LIS of I as the maximum length increasing subsequence ending in AI. Then we can just look at all the indices j before I, such that aj is less than ai, and find LIS of j and add it to ai to make a new increasing subsequence ending in ai. Mathematically, LIS of I is simply 1 plus the maximum of LIS of j for all j before I, such that aj is less than ai. The base case of the recurrence is LIS of 1 equals 1, since the longest increasing subsequence ending in A1 is simply A1 itself of length 1. The final solution, or the longest increasing subsequence of A, is simply the maximum LIS ending in A1, or A2, or A3 up to AN. Mathematically, this is just the maximum of LIS of j for all j. Since the recursive function only has one input I from 1 to n, then we can use recursion and memoization to get a DP solution for the problem. Here's the pseudocode of the algorithm. We start by initializing an empty array LIS of length n. We set the base case LIS1 equals 1 and initialize answer as the maximum of LIS. Then we loop from I equals 2 to I equals n, set LIS I equals 1 representing the sequence ending in AI and being AI only, then loop backwards from j from 1 to I minus 1, and if aj is less than ai, then update LISI as the maximum of LISI, the previous maximum, and 1 plus LISJ. Finally, once we've computed LISI correctly, we take its max with answer, and finally return answer after the two loops terminate. The algorithm takes OFN squared time because there are two nested loops and each of them do OFN work. Great, now let's take a step back. We defined LIS of I as the maximum LIS ending in A of I, and derived a recurrence for LIS. Now let's try to apply the recurrence duality principle, which states that almost any recurrence can be written in two ways, one maximization and one minimization. We already have the maximization solution, so what about the minimization solution? Well, if you spend enough time, you could come up with the definition like this. Let minimum last I of j be the minimum last element in an increasing subsequence of length I from elements A1 to AJ, or just infinity if no such subsequence exists. If you're wondering where the definition comes from, it's just an application of the recurrence duality technique. If you want more experience with it, I encourage you to watch my earlier video about it. that I will link in the description. This definition is useful because if min last I of n is less than infinity, then there is, by definition, an increasing subsequence of length I in the array A. So we simply return the maximum I where min last I of n is less than infinity. Then we're essentially returning the longest increasing subsequence in the array A. However, this is still a problem, because how should we calculate min last I of j? What should the recurrence be here? Again, we defined minimum last of ij as the minimum last element in an increasing sequence of length I in elements a1 to aj, or infinity if no such subsequence exists. Let's take some examples to understand the definition more clearly. Suppose A is again 1, 2, 4, 4, negative 5, 6, and j is 5. So we only restrict ourselves to the first 5 elements of A, which are 1, 2, 4, 4, negative 5. To calculate min last 1j, we consider all possible increasing subsequences of length 1 in A1 to j. There are 4 such subsequences, which are 1, 2, 4, and negative 5. The one with the minimum last element is negative 5, and so minimum last 1 of j is negative 5. To calculate minimum last 2j, we consider all possible increasing subsequences of length 2 in A1j. There are 3 such subsequences, which are 1, 2, 1, 4, 2, 4. The one with the minimum endpoint is 1, 2, and so minimum last 2j is just 2. To calculate minimum last 3j, we consider all possible increasing subsequences of length 3 in A1j. There's only one such subsequence, which is 1, 2, 4. The minimum endpoint is 4, so minimum last 3 of j is 4. There are no increasing subsequences of length 4 or 5 in A1 to j, and so minimum last 4j is equal to infinity, and minimum last 5j is also equal to infinity. Now, one useful way of thinking about minimum last I of j is to consider all possible increasing subsequences of length I in the first j elements of A. The minimum endpoint across all such subsequences is minimum last I of j. Now, going back to the question, how do we calculate the recurrence for minimum last I of j? Well, let's fix j for now and try to calculate minimum last I of j for all I. Since we fixed j, then we can think that we only have the elements a1 to aj in the array for now. Now, consider all increasing subsequences of length I in A1 to AJ. Where is the min last IJ in this case? Well, min last I of j is just the minimum endpoint across all those curves of length I. Now, in those curves, or increasing subsequences of length I, some of the curves end in aj, and some of them don't end in aj. So if we can calculate the minimum endpoint of all curves that end in aj, and all the curves that don't end in aj, and take the minimum of both, then we have calculated the minimum endpoint across all possible curves of length I. Now, what about the curves of length I ending in aj? Well, if we look at the first j-1 elements and delete the last number aj in this sequence, then what do we have? I'm sure if you think carefully, you'll notice that what we have is an increasing subsequence of length I-1 in the first j-1 elements, ending in a number less than aj. But then recall that minimum last I-1, j-1 is the minimum endpoint across all curves in the first j-1 elements of length I-1. And so it must be that minimum last I-1 j-1 is less than aj. So we have the property that if a curve ends in aj, then it must be that minimum last I-1 j-1 is less than aj. As for the curves that don't end in aj, then they're curves of length I in the first j-1 elements. Their minimum endpoint would be minimum last I j-1, the minimum endpoint of a curve of length I in the first j-1 elements. So, to summarize, for the curves that end in aj, their endpoint is aj, but it must be that minimum last I-1 j-1 is less than aj. For the curves that don't end in aj, then the minimum endpoint is min last I j-1. And so to calculate minimum last ij, we simply have to combine both cases. So we have that minimum last ij is equal to the minimum of minimum last I j-1 and aj if minimum last I-1 j-1 is less than aj, or otherwise, then no curve of length I ends in aj, and so minimum last ij is simply minimum last I j-1. Using this recurrence, we can again write a DP solution that takes OFN squared time, but this is still the same as the algorithm from the maximization dynamic program. To improve the algorithm, we need to do a bit more work and make a few more observations. One useful tip when dealing with such dynamic programs is to plot a table for a small input and try to spot some observations in the DP table. So let's do that. Let's again take A as 1, 2, 4, 4, negative 5, 6, and fill in the DP table column by column. Initially, J is 1, so A1 to J is 1. The minimum ending of a subsequence of length 1 is 1, and so min last 1, 1 is equal to 1. Since there are no subsequences of length 2, 3, 4, 5, or 6 in A1 to J, then min last 2, 1 is equal to min last 3, 1 equals to min last 4, 1, and so on until min last 6, 1, which is equal to infinity. Next, we move to the next column where J is now 2, and so we add one new element to the array. Minimum last 2, 1 stays as 1, since the minimum endpoint of an increasing subsequence of length 1 is still 1. However, now min last 2, 2 is equal to 2, since 1, 2 is the minimum endpoint increasing subsequence now. The remaining values are infinity since there are no increasing subsequences of length 3 or more. We keep filling the DP table in this fashion until it's entirely filled in. Now, take a few minutes and try to come up with 2 different observations about this DP table. The observations are critical for you to understand the algorithm coming up. I'm sure if you spend enough time, you'll notice the following 2 properties. 1. Each column is monotonically increasing. But perhaps the most surprising property is that adjacent columns differ in at most 1 value. For example, column 1 and column 2 are exactly the same except for infinity and 2. Columns 2 and 3 are the same except for infinity and 4. Column 3 and 4 are exactly the same. Column 4 and 5 are the same except for 1 and negative 5. And finally, column 5 and 6 are the same except for infinity and 6. Now that we have these 2 hypotheses, let's try to formally prove them. Let's first try to show that each column is indeed increasing. A fixed column means that J is fixed. So for fixed j, we have that for any increasing subsequence in A1j of length I, there's a sequence of length I minus 1 and smaller endpoint. Why is that? Because we can simply remove the last element in a sequence of length I to get an increasing sequence of length I minus 1 and a smaller endpoint. So it must be that the columns are sorted. Now, what about the two different adjacent columns? Well, let's fix column j minus 1 and plot min last I j minus 1 for all I. Let's also plot where aj might be. Notice that the curve drawn is min last I j minus 1. So its values are min last 1 j minus 1, min last 2 j minus 1, and so on until min last n j minus 1. As we argued earlier, this has to be monotonically increasing because it is a fixed column. Let k be the last index where min last k j minus 1 is less than aj. Now let's see how the curve changes when we go from column j minus 1 to column j. What about min last 1 of j? Well, because min last 1 j minus 1 is less than aj, then we already know that there's a subsequence of length 1 in elements a1 to aj minus 1 with endpoint less than aj. Therefore, it must be that the minimum last 1j is the same as minimum last 1j minus 1. Similarly, since min last 2j minus 1 is less than aj, then there's an increasing subsequence of length 2 ending in a number less than aj. So minimum last 2j is unchanged by the addition of aj. This holds for min last 3j and so on until min last kj. Now, what about min last k plus 1j? Well, because min last k j minus 1 is less than aj, then we know that there's a subsequence of length k in the first j minus 1 numbers of the array ending in a value less than aj. Together with aj, they make a sequence of length k plus 1 in the array a1 to aj. So the new minimum last, or the new minimum endpoint for a subsequence of length k plus 1 j is now aj. This is the value that changes from one column j minus 1 to the next. Now what about min last k plus 2j? Well, because min last k plus 1 j minus 1 is greater than aj, then there's no subsequence of length k plus 1 in the first j minus 1 elements with endpoint less than aj. So no subsequence of length k plus 2 exists that ends in aj. So it must be that minimum last k plus 2j is unchanged. This holds for minimum last k plus 3j and so on until minimum last nj. Now, if you look at the curve, you would notice that minimum last ij is exactly identical to minimum last ij minus 1, the previous column, except in one index, minimum last k plus 1j, where k plus 1 is the first index where minimum last k plus 1 j minus 1 is greater than or equal to aj. In addition, its new value is exactly aj. But then this means that we don't really need a two-dimensional array of minimum last ij. We can simply have only one dynamic programming DP array of size n, initially representing the first column of minimum last. In each turn, we increase the column index j and find the one index k plus 1 where dp k plus 1 is greater than or equal to aj, and set its value to aj. As we proved, since the column of min last is always sorted, then dp is always sorted, And so we can binary search in DP to find the index k+1 in O log n time. After updating its value, the new DP table represents the jth column of min last. Here's a dry run for the algorithm on the input 124406. We start with dp1 equals 1 and dpi equals infinity for all I greater than 1, since no increasing subsequence of length 2, 3, 4, 5, or 6 exists in the first one element. Next, we update j forward by 1. We find the first element in the dp table greater than or equal to 2, which happens to be dp2, and update its value to 2. Next, we move j forward and find the first element greater than or equal to 4 in dp. This time it is index 3, so we update its new value to 4 and move j one step forward. This time the largest index, which is less than or equal to k, is index 3. So we update dp3 to 4 and move j one step forward. This time the element in dp that is at least 0 is index 1, so we update dp1 to 0 and move j one step forward. Finally, the first element at least 6 in the array is index 4, so we set dp4 to 6 and move j one step forward. When we're done, we again simply return the maximum index that is not infinity. In this case, there's an increasing subsequence of length 4. Here's some pseudocode to implement this. We first start by setting dp to the first element. Then we loop I from 1 to length of a minus 1, and if the last element of dp is less than ai, then we insert ai to the end of dp, representing the infinity case. Otherwise, we binary search in dp to find the index where dpk is bigger than or equal to ai, and set dpk equals to ai. Finally, we return length of dp as the longest increasing subsequence of a once the loop terminates. This algorithm takes O of n iterations in the loop, and each iteration takes O log n time, so the entire algorithm takes O of n log n time and O of n extra space. I will leave a C++ and Python implementation of the algorithm in the description, but feel free to add other languages in the comments section. Special thanks to the user 0000, since they recommended that I start including implementations of the algorithms in my videos, and so I'll be including implementations in all my videos from now on. Thank you for watching the video. If you enjoyed, please feel free to like the video and subscribe to the channel. And until the next video, I'll see you soon.